Welcome back to Math 104. How does the probability of h given j, the fraction of juniors who are also history majors, compare to the fraction of the whole population majoring in history? Equivalently, how does the probability of being a history major, given that the person is a junior, compare to just the probability of being a history major, period? We compare the probability of h given j to the probability of h itself. To find the probability of h given j, we need to think in terms of drawing randomly one junior from the 200 who are juniors, and asking what's the probability that that junior lives in this region here among the juniors who are also history majors. That equals 60, these 60 students who are both history majors and juniors, out of the 200 who live in the junior circle overall. This is 0.3. This is 30% of the juniors are also history majors. There is a 30% chance that a randomly selected junior is a history major. We compare that to the probability of h in and of itself, and that's going to be a probability out of 1,000. If we select a member of the total survey population, which is 1,000 people, and ask what's the chance that that person is a history major, there are 100 history majors out of those 1,000. So that is a 0.1 probability. There is a 10% chance that a randomly selected survey participant overall is a history major. So what does that tell us? Based on this survey, are juniors more likely or less likely than the general survey population to be history majors? Well, we just found that they are much more likely. We found that the probability that a junior is a history major is 0.3, but the probability that just anybody at all is a history major is only 0.1. Once you have that information, you can start thinking about why that would be true. Probably something to do with the fact that first and second year students haven't declared their majors yet, for the most part. So it's not surprising that juniors would be more likely than the overall survey population to have declared their history majors. In general, if E and F are events, and the probability of F does not equal 0, so F is not impossible, then we define the conditional probability that E occurs given the information that F occurs by the following expression. So the probability of E given F, that's what we're now calling conditional probability, that can be computed as the probability of E intersect F, the probability that E and F both happen, divided by the probability of F. In our survey, the probability of C given J is the probability that a participant lives on campus given the information that this person is a junior. If we compute that according to this formula, then the probability of C given J should be the probability of C intersect J divided by the probability of J by itself. Well, there were 90 people in the overlap region between C and J, whereas there were 200 people in the J circle, and that gives us 90 over 200. That's exactly what we computed before. So applying this formula does actually agree with what we computed earlier. One way of describing this conditional probability is the probability that a randomly selected junior lives on campus, or the probability that a person lives on campus given that he or she is a junior, or the fraction of the junior year participants in the survey who also live on campus. But it's a fraction of the juniors. It's not a fraction of the campus dwellers, it's a fraction of the juniors. We contrast that with the probability of C. This is an unconditional probability. This is an ordinary probability as we've seen it. This probability is just the fraction of all participants who live on campus, or the probability that someone drawn from the full survey population lives on campus. Conditional probability is an important concept. Here's another way of expressing the idea behind it. You perform an experiment and obtain partial information about which outcome occurs. For example, pertaining to our survey, you catch a glimpse of someone's transcript, and you find out his or her class year. You find out whether that person is a junior or is not a junior. Then you know this person's answer to one question on the survey, but not to the other questions about living on campus or being a history major. Knowing this partial information may change your assessment of how likely it is that the participant lives on campus. Here's another viewpoint, another way of saying it. The probability of C equals your old assessment of how likely it is that a survey participant lives on campus. This is without any extra information about him or her. You randomly select someone from the survey population and ask how likely is it that they live on campus. By contrast, the probability of C given J, this is your new assessment. Probability of C was the old assessment. This is now the new assessment of how likely it is that the survey participant lives on campus, in light of the new information that he or she is a junior. If you have partial information, if you find out something new about that person, but a different aspect of that person, like their class here, maybe that gives you a new idea of how likely it is that they live on campus. A major purpose of our study of conditional probability is to understand how your knowledge changes from the old assessment to the new assessment, and whether it changes at all. We have already found the probability of C given J and interpreted what it means. That was 90 over 200, or 0.45. Now let's find the probability of J given C. That means that we're zooming in not on the J circle, but on the C circle. Whatever is the one that we are conditioning on, that's the one that we are zooming in on. So we zoom in on the C circle and regard it as the sample space for a new experiment. We draw from the 600 survey participants who live on campus and ask, what is the probability that one of them will be a junior? That equals 90 over 600. The 90 here is the same 90 we had when we looked at the probability of C given J. And we can see why that is when we apply the formula. The probability of C given J, according to the formula, should equal the probability of C intersect J over the probability of J, whereas the probability of J given C should equal the probability of J intersect C divided by the probability of C. Now notice how the probability of C intersect J and the probability of J intersect C, those are the same thing. So these two probabilities should have the same numerator, but they will have different denominators. This probability turned out to be out of 200, whereas this one is out of 600. Take the formula and keep going. The probability of J intersect C is 90 out of 1000, and the probability of C itself is 600 out of 1000, so this boils down to 90 over 600. That equals 0.15, which gives us the answer to our next question. Does probability of J given C, which equals 0.15, equal the probability of C given J, which equals 0.45? No, not even close. That figures. If they have the same numerator, but different denominators, then as fractions they can't be equal. This example illustrates something important. The direction in which you're doing the conditioning really matters. Typically, when you do a comparison like this, these two conditional probabilities won't be equal to each other. There's another comparison we can do. We can ask, how does probability of J given C compare to probability of J? And what does this tell us? We just computed that the probability of J given C, the probability that a randomly selected campus dweller will turn out to be a junior, equals 0.15. And the probability of J in and of itself, the unconditional probability that a randomly selected survey participant is a junior, that equals 0.2. This is 200 out of 1000. So the conditional probability is less than the unconditional probability. This means that if you find out that somebody lives on campus and ask, now how likely do you think it is that they're a junior? Your estimate of the likelihood that they're a junior goes down when you find out that they live on campus. If you knew nothing about whether they lived on campus or not, and you asked, how likely is it that this person is a junior, the answer would have been 0.2. But in light of the new information that they live on campus, if you find that out somehow, then the new assessment of how likely they are to be a junior drops from 0.2 to 0.15. Some more practice with this. If a student who lives on campus is selected at random, what is the probability that he or she is a history major? So let's stare at the wording here and think what we need to write down. If a student who lives on campus is selected at random, that means we're zooming in on the on-campus circle. we're computing the probability of something given C. So we are asked, given that someone lives on campus, what is the probability that that person is a history major? So this is the probability of H intersect C divided by the probability of C. What is the probability of H intersect C? There are 50 people in the event H intersect C in these two basic regions here. So 50 out of 1,000 is the probability of H intersect C, divided by the probability of C itself, which is 600 out of 1,000. It's okay if you just write 50 over 600 directly, but I want to illustrate that there is a definition of conditional probability, and we can write it down and work with it. This equals 50 over 600, which equals 1/12, or approximately 0.0833. So if you know that someone lives on campus, and then you wonder how likely are they to be a history major, this is how likely, in light of the new information. If you answered this question by just computing P of H, you'd be neglecting the fact that we specifically picked a student who lives on campus. Before going on to the next video, answer the following question. Suppose you do find out that a certain survey participant is living on campus. As a result, in light of this information, are you more inclined or less inclined to think that he or she is a history major than if you hadn't found out that he or she lives on campus?